Now, there are two rules that we're going to look at here called the product rule and the quotient rule. And they get a little more involved, but still not as bad as what you may think. So first, the product rule tells us that if you have a derivative of a product of functions, that's equal to the second function times the derivative of the first plus the first function times the derivative of the second. Now, your book actually has this reversed. It has this term, the f of x times dgx dx, listed first. It doesn't really matter because of the commutative property of addition. I chose to list it this way because of the rule that's coming after this, so that way they're in the same type of format. Either way you write it, whether you have the g of x listed first or the f of x listed first, it doesn't matter. They're still the same thing. So let's take a look at an example here. Let's say we have the function 3x squared plus 6, and that quantity is being multiplied by the quantity x minus 2. And we want to take the derivative of this with respect to x. Well, what this rule tells us is we can simply take the second function, x minus 2 in this case, and we're going to multiply it by the derivative of the first function. Well, if we look at this, we can take the derivative of each piece individually, and 3x squared, the derivative of that is 6x, and the derivative of 6 is simply 0, so it's just 6x. And then we want to add the first function, 3x squared plus 6x, and we want to multiply by the derivative of the second. Well, the derivative of the second, we just have 1x. We keep the coefficient of 1, and derivative of x is simply just 1. So we can look through here and see that, well, let's combine like terms. We get a 6x squared plus 3x squared gives us a 9x squared, and then a negative 12x, and there aren't any other x's over here, so that's minus 12x, and then we get plus 6. And so the derivative of our function here is simply 9x squared minus 12x plus 6, using the product rule. So anytime you have two functions multiplied together, you can follow this product rule. Now, all these rules that I've given you so far, I can derive them for you analytically and graphically. There are some derivations in the book. I'm not going to take the time to do those here in the video, but if you're interested, you can either ask me about it in class or take a look at how the book explains it for you. Now, the last rule I want to take a look at here is the quotient rule. So when you take the derivative of two functions that are being divided, and we have a top function in our numerator and a bottom function in our denominator, it follows this rule that we have listed here on the screen. And if you notice, it looks very similar to the product rule. Actually, the numerator is just one sign away from being the product rule, in that we have the derivative of the second function, the second function times the derivative of the first function, but now we have minus the first function times the derivative of the second instead of plus. So we want to subtract, and all of that is over the denominator squared. Okay, so this is the rule that we have to follow anytime we have a product of functions that we want to take the derivative. So let's look at an example here. Let's say we want the derivative of a function, and let's have x squared minus 3x all over x cubed plus 4. Okay, here's our function, and we want to take the derivative of that with respect to x. So what this tells us is that we take the bottom function, x cubed plus 4, and we multiply it by the derivative of the first, which in this case is going to be 2x minus 3. Now, once again, let's review. Where do we get the 2x minus 3? 2 comes down as a coefficient, decrease the power by 1, so that gives us just an x. We keep the coefficient of negative 3, decrease the power by 1, get a 0, so we're just left with a 3. And then we want to subtract the numerator function, which is x squared minus 3x, and we want to multiply by the derivative of the bottom. Well, that's going to give us a 3x squared. Now, what happened to the 4? Derivative of a constant is gone. It's 0. Okay, now the bottom is simply just g squared. We want to square that bottom function, and in this case, that'll give us an x to the 6th plus 8x cubed plus 16. Okay, that's just expanding the binomial of x cubed plus 4, quantity squared. So when we distribute and we simplify and combine like terms, this simplifies into a negative x to the fourth plus 6x cubed plus 8x minus 12 all over our denominator of x to the 6 plus 8x cubed plus 16. Now, we can't simplify this any by factoring or anything like that, so we just leave it as this quotient right here. So, as you can see, that helps us take the derivative of a function that in the limit process would have been almost impossible. It would have been possible, but very long and tedious in order to do this using the limit technique.